Hello all. Today we are going over a past international GCSE paper, okay? And this one is from May 2025, as you can see in your screens. So it's kind of recent, and it's paper 1P. If anybody knows what this means, I think it has to do with country regions. So this test might be taken in some areas of Europe, and paper one is just taken in Asia or something like that. I don't know. But anyway, let's dive in and start working over the paper. So before we do that, a few general things I always say for papers. This one awards 110 marks and you have 2 hours. Okay, so 2 hours, 100 is 120 minutes, right? For 110 marks. So in your heads, you should calculate or devote or something like that a minute per mark. So if a question awards 10 marks, it should take you about 10 minutes. Okay, don't panic if it takes you 15. Some other question might take you less time. That's fine. And also, when you go through papers, make sure you know what to do. Like, make sure you, before you attempt the problem, make sure you actually know how to solve it. If you don't, skip it, solve something you already know how to solve, and build that momentum and come back and solve the problem that you didn't know how to solve later. Okay, so that kind of helps. And also, they give you a bunch of formulas both in the front page and in the back. Okay, so sometimes just inspecting these formulas in case you don't remember something, or in case you're out of inspiration about how to work out a problem, just come here and check the formulas, and maybe you will get the inspiration needed to solve a problem. Okay, and yeah, these are the general things I always say. So let's dive in with question one. Ice hockey is a team sport played on ice. Players try to hit a disc called a puck into the other team's goal. Let me know in the comments if anybody ever played hockey, by the way. It seems really hard to me, for me. So, question A, diagram 1 shows a puck traveling across some smooth ice. State the formula linking average speed, distance moved, and time taken. So this, of course, this is an easy one. So average speed is distance over time, right? Distance over time, and I think they actually give you this formula in the back of the paper. So anyway, part two. The puck travels at a constant speed of 2.8 meters per second. Calculate the distance moved by the puck in a time of 3.5 seconds. Okay, so from what we just wrote, we can use, I'm going to write B for simplicity. So D is speed, which I will denote by V times time. Okay, so 2.8 meters per second. By the way, when I work out problems, I try to reach a final formula, a final algebraic formula, if you will, and then I plug in numbers. Okay, so when I plug in numbers, I put all the numbers to the left and all the units to the right. Okay, this helps with manipulating both numbers and units. Anyway, so velocity is 2.8 meters per second, time is 3.5 seconds. So you see that seconds immediately cancel, for example, in this case, okay? And the distance works out to be 9.8 meters, okay? Which is our answer. Let's move to part B. Diagram 2 shows a puck traveling across some rough ice, okay? And the direction of travel is to the right. The rough ice exerts a frictional force on the puck. Draw a labeled arrow on diagram 2 to show the force of friction acting on the puck. So frictional forces resist motion. Let's use, this is pink. Okay, I like it. So we're going to use pink to denote the frictional force. So the frictional forces always act in the opposite direction of the motion, of the velocity. Okay, so the frictional force here is this one. Okay, we usually draw it at the bottom of the object. Okay, I don't think if you do this, if you draw the force at the starting from the center of mass, I don't think they will subtract points from you. But yeah, I mean, usually you draw it at the bottom of the object. Okay, so this is our answer. And now part two, explain how the force of friction changes the velocity of the puck. So it will reduce the velocity of the puck. So the speed. Okay, I'm gonna try to make to improve my handwriting. Okay, so the speed of the puck decreases. Okay, and this is because the frictional force acts in the opposite direction from the motion. Okay, so I'm going to write this down. So this is because the frictional force acts in the opposite direction to the motion of the puck. Okay, so the resultant force reduces. Okay, so what we mean by that is that if there is a force that kind of makes this puck move to the right, then with the addition of the frictional force, so if we only had this force, let's call it, I don't know, P, okay? The sum of all forces will be P if that was the only force acting. But now with the friction, the total force is going to be P minus F. So it's going to be reduced, okay? And remember that the total force is mass times acceleration, right? So this means that the frictional force reduces the speed of the puck. All right. I think this is it, yeah, for question one. It awards 7 marks. So let's move on to the second question. Okay, question two. This question is about astrophysics. I mean, as it's stated right there. Diagrams A, B, C, and D show different orbital paths for object Y orbiting object X. Okay. Table 1 gives some possible names for object X and object Y. Complete the table by placing one tick in each row to show which orbital path is correct for each combination for object X, and object Y. Each orbital path may be used once, more than once, or not at all. So all possible options, pretty much. Okay, I mean that's not very helpful, but okay, let's see. So the Earth and the Moon. I mean, this is an easy one. Can you pause the video and actually guess? So it's gonna be option A, right? Okay, circular orbit with X being the Earth and Y being the Moon. Now, object X and object Y are the Sun and a comet. So a comet goes really close to the Sun, where it travels really fast, and then it goes really, really far out. So it can even reach like the farthest objects. Is it called the Kuiper belt? The one that is really outside the planetary system of our solar system. So this is going to be option B. So this is what I'm trying to say. Okay, and this is because comets they will come really close to the sun and then travel really, really further outward towards the Kuiper belt. Okay, so yeah, okay, that's option B. By the way, a few months ago, I bought this astrophysics simulation kind of game, and I already had a video showing some things that you can do with that program. So maybe in the future I will do more with that. I even forgot the name of the program I bought. Universe Sandbox. Okay, I remembered it. So yeah, I mean, in that program you can actually send comments towards the Earth and see what's going to happen and stuff like that. So anyway, and then the other combination is the Sun and the Earth. That's going to be orbit A. It's very similar to the orbit of the moon around the Earth. It's almost circular, okay? All right, so let's move on. Part 2. Give the name of the force that causes one object to orbit another object in space. So that's the gravitational force, of course. So let's write that down. Gravitational force. Okay. Now, part B, table 2 gives information about 4 different stars in the same galaxy as the Sun. Give the name of the galaxy that contains the Sun and the stars shown in table 2. That's the Milky Way. Okay. And if you guys ever travel to where I am right now, to Cyprus, because the summers are kind of really hot and clean, so the atmosphere is clean, you can actually see the Milky Way during the summer. It's if the night is really clean, and if you are outside cities, so it's really dark, so you can actually see it, and it's kind of impressive, the Milky Way. Okay, let's move on to part 2. Explain how the stars in table 2 can be classified according to their color. Okay, so classified in terms of temperature is my assumption about what they actually ask here. So the coolest will be the red star, okay, because you have to remember that red. Okay, so you have blue at about 400 nanometers, and 700 nanometers is red. Okay, and then in between you get yellow and white. So blue white will be somewhere there, for example. White will be somewhere there, and then yellow will be towards the red. Okay, so um, so the red star will be the coolest, pretty much, and the blue-white star Vega will be the hottest. Okay, and in your book, from what I checked, you actually learn about the classes, various classes O, A, B, whatever of stars. I think this is not what they ask here, and let me actually check the mark scheme. I have it here in front of me, though I don't really use it. Yeah, they ask to classify in terms of temperature. So let's do that. So the color of the so the color of the star, um, depends on its surface temperature. Okay, Antares is red, making it the coolest of the 4 stars. Okay, in order from coolest to hottest, we have, and let's do Antares first, is the coolest because it's red. Then it comes Capella. I actually never heard of these stars except Vega. So Capella, which is yellow. Oops. So yellow, kind of like it's kind of like our sun. Okay. Then you have Sirius B. Oh, I know Sirius B too. Okay, which is white. And then finally Vega, which is blue, white. And another thing to classify stars is, of course, the evolutionary state. Okay, so for example, we know that the red supergiants. I forgot to mention this while actually solving this. So red supergiants burn all their hydrogens and expand, so they're cooler. Okay, then main sequence stars are usually very hot. So Capella and Vega are main sequence. And Sirius B is a white dwarf. These stars are also hot. Okay. So yeah, I mean that's another way to tell to classify stars. Okay. This is done. Let's move on to the next question. Okay, question 3. Describe the likely future evolution of Antares. So this is the red supergiant star we just mentioned. So main sequence stars burn hydrogen and convert into helium in their core, but then red supergiants have burned all of their hydrogen. So they eventually undergo the supernova explosion. So let's write that down. Antares will undergo a supernova explosion. The remnant core, okay, so whatever remains, the core of the star, so the remnant core will collapse into a neutron star. Okay, if the remaining mass is large enough, okay, it will collapse further into a black hole. So it will collapse further into a black hole. So we are talking about usually if the mass is larger than or equal to about 3 times the mass of the sun, okay, uh, these stars eventually become black holes. Okay, but I think you don't learn that at the GCSE level, so I'm gonna erase that. Okay, right. Part 4. Describe what additional information is needed to predict the next evolutionary stage of Vega. So we need to know Vega's mass relative to the mass of the sun, because the future evolution depends on its mass. So since Vega is a main sequence star that is blue, it means that it's a giant star probably, okay? So, but we need to know its mass to be able to tell what's going to happen to it, okay? All right, so this was question 2. Let's move on to the next question. Question 3 is a circuit problem. So a student builds this electric circuit to measure the temperature of a room. At 20 degrees Celsius, the voltage across the thermistor is 3.9 volts. Explain why the reading on the voltmeter is 2.1 volts. Okay, so they tell us that the voltage across the thermistor, let's call it V1. So V1 is 3.9 volts, but you immediately see there that you have a 6-volt power supply. So 3.1 plus 2.1 is 6 volts, as it should, because this is a circuit in series. And because I got a question once, so in series means that the same current goes through both elements, okay? So you see that if you imagine current being water, it will just flow from the thermistor to the resistor and then back to the power supply, okay? So let's write that down. So the components are connected in series. So the voltages across them, must add up to the battery voltage at 6 volts, okay? So 6 minus 3.9 is equal to 2.1 volts, which is the voltage that the voltmeter will record, okay? And let me erase all this. Okay, and let's move on to part 2. The resistor in the circuit has a resistance of 290 ohms. Calculate the current in the resistor, and they actually give you the formula. Okay, so current is voltage over resistance. Okay, so this is 2.1 over 290, which yields 0.0072 amps. Okay, state the reading on the ammeter. Okay, so that's the ammeter, and it's gonna of course be 0.0072 amps, because the current is the same everywhere in the circuit since it's a series circuit. Okay, all right. For calculate the resistance of the thermistor. So the resistance of the thermistor is going to be the voltage across the thermistor over the current, which is the same as the current everywhere in the circuit, as we just said. So this is going to be 3.9 over 0.0072, which yields 541.7 ohms, which is about 542 ohms. Okay, that's our answer. Let's move on to part B. The student observes that the voltmeter reading increases as the temperature of the room increases. Explain this observation. So just to remind you, the circuit looks like this. So they tell us that this voltmeter indicates that the voltage increased across the resistor. So why is that? So let's write down a few things. So as the temperature of the room increases, okay, the resistance of the thermistor actually decreases. Okay, so this causes the current in the circuit to increase. And why is that? Because we need the current. So the current is equal to the voltage that we have, which is 6 volts in this case, over the total resistance. Okay, so since the resistance of the thermistor decreased, actually, okay, let me spell it out. So the total excuse me, the total resistance is R plus R of the thermistor. Okay, so if the R of the thermistor decreases, the current increases. Okay, okay, so the resistance of the fixed resistor does not change, right? Okay, and since voltage is current times the resistance of that resistor, okay, a higher current means a higher voltage across that resistor. Okay, so the voltmeter reading increases. Okay, maybe it's an overkill that I've written so many things, but I try to be thorough. Okay, now let's go to part 2. The student wants to use the circuit as a temperature measuring device. They have this additional equipment, a large beaker, water at different temperatures, a thermometer. Describe what measurements the student needs to take so that the circuit could be used as a temperature measuring device. Assume that the thermistor in the circuit is waterproof. You may draw a diagram to help your answer. I'm not going to do that. So let's describe what we need to do. So place the thermistor and a thermometer into the beaker of water. Okay, vary the temperature of the water via heating, for example. Okay, you need to steer the water so temperature is homogeneous. Okay, as I keep going, my handwriting deteriorates, guys, so I'm gonna try again. So steer the water so temperature is homogeneous. Okay, record the voltmeter reading at each temperature. Okay, plot a graph of the voltmeter reading against temperature. Okay, and then you can use the graph. Use the graph. Okay, to find T corresponding to a certain V. Okay, so it's kind of an involved problem, but you need to write all these things to describe it perfectly for the grader, I guess, or something like that. So this was question 3. Okay, let's move on to question number 4. Okay, question number 4. This question is about the process of controlled nuclear fission in a nuclear reactor. Okay. Question A. In a nuclear reactor, uranium-235 nuclei are split to produce daughter nuclei and neutrons. State what else is released in nuclear fission that makes the process useful in a nuclear reactor. Okay, so thermal energy pretty much. Okay, thermal energy, which is what makes this process energetically useful, right? Okay, I think that's enough. Part B, what is the function of the control rods in a nuclear reactor? So the control rods absorb excess neutrons pretty much. Okay, so option A is the correct one. And they are absolutely needed to absorb extra neutrons so that the reactor doesn't explode pretty much. Okay, so is there anything else I want to say here? I think not, but I mean, you guys know the general idea, right? So you have uranium-235. You hit it with a neutron, okay, and it splits this nucleus into, I don't know, something lighter, and then you have the release of extra neutrons that go on to find other nuclei to split pretty much. So this releases heat, and this is what makes a nuclear reactor useful for the production of energy. Okay, C. What is the function of the moderator in a nuclear reactor? So change protons into neutrons, that's crazy. No. Change neutrons into protons, again, it's crazy. Actually, neutrons change into protons by themselves. I mean, they decay into protons when they are free, not inside nuclei, okay? So, no, that's wrong. Then C, slow down neutrons. This is actually what the moderator does, okay? Because fast neutrons are hard to manage and they don't really help in splitting nuclei. So you need to have thermal neutrons, if I remember my nuclear reactor physics well. So yeah, C is the correct answer. And definitely you don't want to speed up neutrons, okay? Let's move on. D. Many of the daughter nuclei produced in nuclear fission are very radioactive. These daughter nuclei decay by emitting ionizing radiation in a random process. State what is meant by the term ionizing radiation. So, this is radiation, okay, that can ionize atoms, which means removes electrons from atoms. Um, okay, is there anything else? Removes electrons from atoms, turning them into ions, pretty much. Turning them into ions. Okay. Two, state what is meant by the term random process. So it, it is impossible to predict when any particular nucleus, when any particular nucleus will decay. Okay, that's the answer to part two. Part three, the diagram shows some parts of a nuclear reactor. So we see the shielding, the coolant out, the coolant in, and the reactor vessel. Explain the role of shielding in a nuclear reactor. So the radiation produced inside the reactor is harmful to tissue, to living tissue. Okay, so the shielding absorbs the radiation before it can escape. Okay, this reduces or eliminates the amount of radiation that reaches workers in the surrounding area. Okay, so the biggest problem with these reactors are neutrons. Okay, so to shield something from neutrons, you need material that is heavy, really heavy, like lead or lots of water or anything that can absorb the kinetic energy of neutrons, because neutrons are not charged. Okay, so they are like balls, like billiard balls flowing around. So you need to put material, like for example, if you put water has a lot of protons, right? So these neutrons, let's make them red. Okay, so these neutrons will collide with protons, so their direction of motion will change. So via various collisions, they eventually lose their energy and stop. Okay, so that's why you need shielding. And in case they haven't told you in school, neutrons are the most dangerous guys because they are not charged. They can penetrate matter. They can convert. They can ionize. They can break atoms, molecules, bonds. They're really dangerous. Okay, so this was question 4. Let's move on to the next question. Okay, the next question is about electric motors. So the diagram shows a simple direct current DC electric motor, and we see the magnets and the coil and the split ring commutator and the brushes that bring the current in. So just to walk you through what's going on here, so you have the current entering from there, and then it enters the coil and goes around like that. Okay, or maybe it's in the other. Yeah, they actually show us the direction. Sorry, so that's the direction. Okay, so if you to find the direction of the induced magnetic field due to this current, you can curl your fingers around I, and then your thumb is going to point towards the direction of the induced B. So B is going to be downwards like that. Okay, and then of course this coil turns. Okay, and as it turns, eventually it encounters these gaps here at the brushes that help with the direction of the current remaining constant. Okay, so it kind of resets, so that's a gap there. Okay, so as this it's really hard to explain from the internet, I mean from my iPad, but internally this wire touches pretty much this commutator, so it remains in contact until it encounters the gap, okay, and the gap pretty much allows the direction of the current to remain constant inside that coil, okay, because once it reaches the gap, the then the coil loses touch with the commutator there at the gaps, so it resets pretty much and it goes back to where it started. So the current remains in the direction I'm showing over there. Okay, I hope this explanation helps. If it doesn't, ask me in the comment section, and I'm gonna provide further explanations if needed. So let's go read the question actually. Okay. Explain why the coil turns continuously when the motor is connected to a direct current supply. You should refer to the brushes and the split ring commutator in your answer. So let's start by stating that the current flowing through the coil creates a magnetic field, creates a magnetic field, okay, around it, making the coil behave like an electromagnet. Okay, so making the coil behave like an electromagnet. Okay, and I mean, we explained it earlier. So if you have a coil like this, okay, and there is a current flowing in this direction, then the magnetic field, again, using your right hand, curl your fingers around the coil, then the magnetic field will be into the page. Okay, so that means into the page. If the current is instead flowing in the opposite direction, okay, so let's draw the situation again. So if the current was flowing in this direction, okay, then if you put your fingers, if you curl them around I, you will see that your thumb points outwards. So in this scenario, B is going to point outwards, okay? So in case you haven't been taught this in school, this means an arrow coming towards you, so out of the page, whereas this symbol means an arrow going into the page, okay? So you kind of see the tail of the arrow, okay? So yeah, that's the situation. Let's erase this and move on. So the second thing we need to write is that this electromagnetic field, this actual magnetic field, I mean the induced magnetic field. So this magnetic field interacts with the field from the permanent magnets, okay, producing a force on the coil. Okay, so the way to understand this is, let me try. Okay, so if these are the electromagnets, I mean the permanent magnets, okay, and this is the coil, okay, and then there is a current in this coil, okay, then you have to use Fleming's left-hand rule. So if the direction of B is to the right, okay, so if B is to the right, the magnetic field is to the right, then you put your index finger in the direction of B, okay, and then you put your middle finger in the direction of I, and then your thumb is going to point towards the force, okay? So, and another detail is that if B is parallel to I, then the force is 0, okay? So this may be going a little bit outside what you learn at the GCSE level, but I hope it's understandable, okay? So what I'm trying to say is that let's put our index finger pointing to the right, and we're talking about the left hand index, okay? Then if we put the middle finger, so if we come to this side of the coil, if we put our middle finger down, then we will see that our thumb points outwards. So you have an upwards force on that side of the coil. And if you go on the other side of the coil, since current on this side of the coil points up, we have to reverse the direction uh, of the current. Therefore, the force on this side is actually down. Okay, so you have a pair of forces that kind of rotate this thing around. Okay, so I hope this makes sense. Let me know if it actually goes a little bit outside what you learn in school. But this is the explanation. But I'm gonna erase it because I feel like it's distracting a little bit. So I'm gonna erase it and continue. So we talked about the force. So now let's talk about the brushes a little bit. So the brushes maintain electrical contact, okay, between the external circuit, and the spinning coil, okay, allowing current to keep flowing without the wires tangling. And the external circuit is this one. I mean, whatever they use to provide current to the circuit, okay? To the coil, excuse me. Yeah, okay. The next thing we need to write, let me use a clean page because I ran out of space. Every half turn, okay, when the coil is vertical, the split ring commutator, okay, swaps which side of the coil is connected to which terminal. So this is what's happening. So internally, so if that's the wire that touches the commutator, so it rotates until it reaches this gap, pretty much, okay? And then it, of course, keeps spinning there. But once this side of the coil spun all the way to this gap, okay, and then made it to the other side, now the current on this side comes in this direction. But once it makes it to the other side, the current reverses direction, right? Because because whatever the function of this was is now the function of this wire, okay? Because at the same time, this wire keeps spinning down, and then it makes it in the gap, and then makes it to the other side. When it comes to the other side, the current enters from this side, okay? So basically that commutator helps, I mean, if you had to do that manually, you will tangle the wires all the time. So this kind of does this automatically. I don't know if I'm explaining it properly, but you have to use a little bit, I mean, your imagination, or maybe you use some videos that they actually show this mechanism. I can't show them here because I'm going to run into copyright problems, but I hope it makes sense. So the wire extends into this ring pretty much, right? And it touches. So it rotates up. Since the current comes on this side, right? Then the current keeps entering the circuit in this direction for this wire. But when this wire makes it through the gap and makes it to this side, okay, now this wire that initially received the current now takes the current away, okay, so it makes it to the other side, and then the current goes in the other direction, okay. So this is the explanation I have. I hope it makes sense. I'm pretty sure it's confusing because it's really hard to describe it on an iPad, but I hope it makes sense. So let's go back. Okay, we talked about the half turn thing. So this reverses. the direction of the current in the coil. Okay. And then reversing the current, reverses the direction of the force on each side, okay, of the coil, which keeps the coil turning in the same direction continuously. Okay, so I think this one was kind of a hard problem because it's difficult to explain in words, but okay, I hope this makes sense. This was question 5. Let's move on to the next one. Okay, question 6 actually appeared in a recent video I made. So a lot of people ask me to make videos about modular GCSE physics, and there was a problem that was identical to this one. So I'm gonna have to go over the same problem twice. But okay, this is a different video, so let's go over it. But I guess they used problems from these papers into the modular papers or something like that. Anyway, so two students do an experiment to determine their power when running up a set of steps. The diagram shows how they set up their experiment. Not all of the steps are shown in the diagram. This is the student's method, okay, and they give us a description. Student A stands, with a stopwatch at the top of the steps. Student A starts timing on the stopwatch and shouts "go" at the same time. Student B begins to run up the steps when she hears student A shout. Student A stops timing when student B reaches the top of the steps. The student repeat their method 2 more times. Give a reason why the times recorded may not be accurate. So reaction time is the answer, I guess. So student A has a reaction time. Okay. So there will be a delay between student B reaching the top and the stopwatch being stopped. Okay. Similarly, there will be a delay at the start. Okay, this was question A. Part B, there are 24 steps in total and each step has a height of 19 centimeters. Student B has a mass of 67 kilograms. Show that student B gains about 3,000 joules of energy in her gravitational store when she runs up the set of steps. So GP is mass times G times height, right? So the mass in this case is 67, G is 10. The units are kilograms for mass, meters over second squared for G, and then the height is 24 steps times 0.19 meters for each step. So the final answer is 3055.2 joules, which is about 3000 joules. And 1 joule is 1 kilogram times meter squared over second squared. Okay, this might be an A-level thing, so you don't really need to know the base units and stuff like that. So anyway, let's go to part 2. The table shows the times recorded for student B. Calculate the mean time from this data. Give your answer to 3 significant figures. Okay, so the average time is going to be 4.28 plus 4.95 plus 4.65 over 3. So this is 4.63 seconds. Okay, part 3. Calculate the mean power of student B transferring energy to her gravitational store as she runs up the steps. So power is energy over time. So the energy is 3055.2. Time is 4.63 joules per second. So we get 659.9 watts, which you can write as 660 watts. Okay, so about 10 light bulbs. I mean, just to help you, I mean, old school light bulbs, not the modern LED ones. So uh, that's a lot of power, kind of. So let's move on. C. The students extend their investigation by calculating the power for students of different masses running up the steps. The graph shows their results. They are all over the place, okay? The students conclude that the greater the mass of the person, the greater the power of the person when running up the steps. Comment on the student's conclusion. Okay, so first of all, we just have 4 data, and then we have this wild jump from 50, whatever it is, 55 kilograms to 68 kilograms. So we don't have enough data points there, and we don't have a lot of data points here, and we are missing lots of data points. So we cannot really tell what's going on. So first of all, there are not enough data points to draw a reliable conclusion. Okay, that's the first point. A wider range of masses should be tested. Including values between those already tested. So between those already not tested, let's say measured. Okay, that's better. The first data point at 55 kilograms, as we just said. Okay, could be anomalous because there's a very wide jump. So yeah, I mean, we go from 600 and say, what is that, 20 maybe watts to 920 watts. So it's a wide jump. Okay, so not a reliable point. Let's use a clean page. The last 3 points, the last 3 data points, okay, show approximately the same power suggesting power may be independent of mass. Power may be independent of mass. For that range. I mean, you can kind of draw a straight line there, right, to fit the data. So it seems like it's independent of mass, actually. So yeah, that's another problem. And then we can also write that the person with the greatest mass okay, so around 100 kilograms does not produce the greatest power. Okay, so I mean, for these 3 data points, okay, and I mean including this one. So yeah, I mean, the idea is that the heavier person should have the most power, but that's not the case. Okay, this was question 6, so let's move on to the next question. Okay, question 7. This question is about pressure. Small air bubbles form in a container of water. The pressure of the water acts on these bubbles. The diagrams, show the forces that cause this pressure. Which diagram correctly shows how the pressure of the water acts on a stationary air bubble? Okay, so that's the key, stationary. So if it's stationary, the forces should be the same throughout. Okay, so that's the case for option D. Okay. Yeah, I mean, because it's stationary. Okay, if it wasn't stationary, we will need something different, but okay, let's move on. Part 2, the diagram shows the air bubbles rising to the surface of the water in a container. Explain why the bubbles increase in volume as they get nearer to the surface of the water. Assume that the temperature of the water is the same throughout the container. So, okay, we can write that as the bubbles rise closer to the surface. Okay, the depth of water above, them decreases, right? Okay, so there is less weight of water pushing them down. Less weight of water pushing down. Okay, I will need a clean page. This means the pressure acting on the bubbles decreases. Okay, since pressure and volume are inversely are inversely, let me fix this, inversely proportional actually P1 V1 is P2 V2 at constant T. Okay, as the pressure decreases, the volume of the bubble increases. Okay, and that's our answer. Let's move on to part B. Too many questions where you have to write things instead of calculating things, I have to say, for the GCSE papers. So a teacher does a demonstration using an inflated balloon and a board with many sharp nails. The teacher pushes the balloon onto the board of nails. The balloon does not pop. The teacher then pops the balloon using a single nail. Explain why the balloon does not pop when pushed onto the board of nails. So the board of nails spreads the force over a much larger surface area than a single nail. Okay. Since let's use a clean page again. So since pressure is force per area, okay, for the same applied force, okay, a larger area means a lower pressure at each nail tip. Okay, and finally the pressure at each nail, okay, is too low to pierce the balloon. And that's our answer. Maybe it's a little bit of an overkill, but I hope you get the idea. And also, this is how I think in India there are people who sit on a bed of nails. So that's the same principle there. So if you stand on one nail, you're a dead man. But if you lay flat on it, you're okay. In theory, I wouldn't do it. Okay, I wouldn't do it. But I mean, people do these kind of things. So let's go to the next question. Okay, question 8. A student uses a ripple tank to investigate water waves. Diagram 1 shows the ripple tank when viewed from the side. Okay, so you have this thing moving up and down, and it makes the water oscillate, I guess. So you have waves forming on the water. A dipper moves up and down to produce waves on the surface of the water in the container. The waves, on the surface of the water are transverse. State what is meant by a transverse wave. You may draw a diagram to help your answer. So, a transverse wave, transverse wave is one where the oscillations are perpendicular okay to the direction the wave travels. Okay, so in this case, for example, the oscillations are going to look like that, but the wave travels to the right. Okay, so these two things are perpendicular. All right, part B. Diagram 2 shows the surface of the ripple tank at an instant in time when viewed from above. The dipper produces circular waves on the surface of the water. 1 centimeter in diagram 2 is equal to 2 centimeters in the laboratory. Use the diagram to measure the wavelength of the water waves. So, okay, so I have to bring up the ruler. It's one of my least favorite activities to do when I film these videos, but anyway, you can easily see that that's from there to there, it's 1 centimeter, right? I mean, the same goes from there and there. So 1 centimeter, which means that the lambda is 2 centimeters, right? Um, so that's 1 centimeter. So lambda is 2 centimeters because they tell us that. Okay. 2. The dipper moves up and down with a frequency of 15 hertz. Calculate the speed of the waves. So the speed is lambda times the frequency. So 2 times 10 to the negative 2 meters times 15 hertz, which is seconds to the minus 1, yields 0.03 meters per second. So 0.03 meters per second is our answer. So let's move on. The student then makes the dipper move horizontally to the right at constant speed. So, I mean, we see the motion, okay, to the right. Okay, the dipper continues to move up and down with a frequency of 15 hertz. Diagram 3 shows the surface of the ripple tank at an instant in time when viewed from above. Okay. Explain how the frequency of the waves arriving at point X compares with the frequency at which the dipper moves up and down. Okay. All right, so we can write that the frequency at point X, is greater than the frequency at which the dipper moves. So it's greater than the frequency the dipper moves. Okay, this is because the deeper is moving towards X. Okay, so the wavefronts ahead of it are compressed. Okay, closer together, are compressed closer together, meaning the wavelength, okay, in that direction is shorter, which is kind of what you can see. I mean, the wavelength there is shorter than what the actual wavelength is, okay? Let's move on. A shorter lambda means more wavefronts arrive per second, so the frequency is higher. Okay, the speed of the wave, though, the speed of the wave does not change. Only the wavelength. So this is actually the Doppler effect, in case they don't tell you. I think they probably tell you at school, but this is the Doppler effect, okay? All right, let's move on to the next question, okay? Okay, question 9. A productinium generator is a device that can produce samples of an isotope called productinium-234M. By the way, since I'm a nuclear physicist, okay, M means metastable. So it's a special term used in nuclear physics to describe some situation in which a nucleus is kind of stable but not really stable, okay? So it remains stable for a large amount of time but not forever. So anyway, a teacher investigates the activity of productinium-234M using the apparatus shown in the photograph. There's a radiation detector, a productinium generator, okay? Question A, the teacher uses a radiation detector to detect the radiation emitted from the productinium-234M. Give the name of a suitable radiation detector. That's the very popular a Geiger Mueller tube. Okay, B, give 2 safety precautions to minimize the risk of harm to the teacher from the radiation emitted by the productinium generator. So increase the distance between the teacher and the source. Okay, so that's one. And handle the source with tongs rather than your hands. Okay, let's move on. C, productinium-234M decays with half-life, of 70 seconds. The initial count rate is 840 counts per second. Calculate the expected count rate after 140 seconds. Okay, so you start with 840 counts per second. So in one half-life, which is 70 seconds, okay, you will have half of that, so 420 counts per second, and then in another 70 seconds for a total of 140. That's the second half-life, so you will have a halving again, so 210 counts per second is our answer. Okay. Part 2, the activity of an isotope is the total amount of radiation emitted each second. The teacher estimates that only 5% of the total radiation emitted is detected by the radiation detector. Estimate the activity of the isotope when the count rate is 840 counts per second. So if you go to this device here, okay, so if the source is down there, it emits radiation in all these directions, right? Equally. Okay, so only a small portion of this radiation enters the detector, and they tell us that's 5%. So whatever passes through this window is what is captured. Okay, and they tell us that that's 5%. So all we have to do is to divide by that to find the total, right? So 840 over 5%, which is 0.05, yields 16,800 counts per second, which is also known as becquerels. So here you can write 16,800, and then becquerels is this unit. Okay, becquerels means 1 BQ, becquerel is 1 count per second. Okay, this was question 9. Let's move on. 10. A student investigates the magnetic force on a current carrying metal rod. The student places a U-shaped magnet on a sensitive balance. They connect the rigid metal rod to a low voltage power supply and then fix the rod in place so that it passes between the poles of the magnet. The diagram shows part of the student's apparatus. Okay. When there is a current in the metal rod, the rod experiences a force due to the magnetic field of the magnet. The reading on the balance changes because the magnet experiences a force that is the same magnitude as the force on the rod but in the opposite direction. The student can increase the current in the metal rod up to a maximum of 5 amps. Suggest why the student should only have the power supply switched on for short periods of time. Okay, so the problem is that the current will hit the rod. So current will hit the rod. Okay, that's the problem. So this risks the rod or power supply overheat and cause burns. Okay, B. Before the power supply is switched on, the reading of the balance is 194, 0.95 grams. After the power supply is switched on, the reading of the balance is 193.80 grams. Calculate the force exerted on the current carrying rod by the magnet. Okay, so we basically have to subtract these two values pretty much. So the force is going to be 194.95 times 10 to the negative 3, because we have to convert to kilograms, that's given in grams, okay, times 10 minus 193.80 times 10 to the negative 3 times 10. This yields 0.012 newtons, which is the answer. Okay, simple as that. Let's go to part C. The student investigates how the balance reading varies as they change the current in the metal rod. The table shows the student's results. Okay, plot the student's results on the grid and then draw the line of best fit. Okay, so this is going to be a little bit tedious. I'm going to show you 2 pairs of values and then I'm going to speed up the video for the final result. Okay, so the first pair is when the current is 0, we get 194.95. So let me think. I need to use my calculator really quick. So each small square is 0.025 grams. Okay, so we need 194.95. So it's going to be this point over here, right? Is that correct? Let me see. Yeah. Yes, that looks correct. So that point, and then the second pair 0.5 and then 194.80. Okay, so that's gonna be that point. Okay, now I'm gonna speed up the video. Okay, these are all the data points. Now we have to draw the line of best fit. So we start from the first point, draw a line. Okay, so the line has to pass through all the data points. So something like that looks good. Okay, passes through all the data points. You should have as many points to the left of the best fit line as you have to the right, and symmetrical. So that looks good. Okay, all right. Part 3, the student changes the connections between the metal rod and the power supply to reverse the direction of the current. Draw another line on the graph to show how the balance reading will vary with current after this change has been made. Okay, so now the balance reading will increase as we increase the current, starting from the same point. So our first data point is the same. And then the last data point, remember that we have a decrease of 0.9 between the first point. So I'm trying to say that this distance is 0.9 between the first data point and the last data point. Okay, so we're going to have the same change, but it's going to be an increase this time. So the first data point is the same at 0 current. And then the last data point is going to be 194.85, which is this point, plus 0.9, but in the positive direction. So 194.85 plus 0.9, it's going to be 195.75 at 3 amps. So up here, pretty much, okay? And we have to draw a line connecting these 2 points. Okay, so this is kind of like the symmetric graph, but in the other direction. Okay, so I hope this makes sense because this time we will have an increase in the mass pretty much. Okay, so this is our answer for question 10, and we are ready to move on to question 11. Okay, fluorescent tube lamps can be used in schools and office buildings for lightning, excuse me. The photograph shows an engineer installing a fluorescent tube lamp. Okay. Diagram 1 shows a simplified view of the components of a fluorescent tube lamp. Okay. When the lamp is on, a large voltage is applied between the positive electrode and the negative electrode. State what is meant by the term voltage. So voltage is energy per charge. Okay. Is the energy transferred per unit charge per unit charge that passes through the component. Okay. 2. The large voltage causes electrons to accelerate from the negative electrode towards the positive electrode. An electron gains 1 times 10 to the negative 16 joules of energy when it accelerates between the electrodes. Show that the voltage between the electrodes is about 600 volts. And they give you the magnitude of the electron charge as 1.6 times 10 to the negative 19 coulombs. Okay, so energy is charge times voltage. So voltage is energy over charge. So 1 times 10 to the negative 16 joules over 1.6 times 10 to the negative 19 coulombs yields 625 volts. 1 volt is 1 joule per coulomb, and that's about 600 volts. Okay. 3. The electron gains 1 times 10 to the negative 16 joules of energy in its kinetic energy store when it accelerates from the negative electrode to the positive electrode. Calculate the speed of an electron when it reaches the positive electrode. Assume the electron is initially at rest. Okay, so the kinetic energy of the electron, okay, is going to be equal to the energy of 1 times 10 to the negative 16 joules of gained energy, right? So, so the velocity is going to be 2 times the gained energy over its mass, and we have to take the square root of that. So we have the square root of 2 times 1 times 10 to the negative 16 over 9.1 times 10 to the negative 31 kilograms, which yields 1.48 times 10 to the 7 meters per second, which is about 1.5 times 10 to the 7 meters per second. Okay. B. When the electrons accelerate between the electrodes, they collide with mercury atoms. Okay. Energy is transferred to the mercury atoms during the collisions. This causes the mercury atoms to emit UV light. Atoms in the fluorescent coating absorb this UV light, which is then re-emitted as light from a different part of the electromagnetic spectrum. Diagram 2 shows the process. So inside the tube, we have electrons hitting the much larger mercury atoms. They cause them to emit ultraviolet light, which is absorbed by the coating and then re-emitted as visible light, okay, on the outside of the tube. Question I, suggest why the tube must have a fluorescent coating for the lamp to operate effectively. Okay, so UV light is not visible by Homo sapiens, I mean by humans, okay, by humans. I think bees actually see UV lights, but please check and let me know in the comments, okay? And I think there are other animals that see kind of like UV light. Some animals see infrared light, but we don't. So yeah, bad luck. So the fluorescent light, sorry, the fluorescent coating, excuse me, the fluorescent coating absorbs the UV light, okay, and re-emits visible light, okay, which is what we see. I mean, without the coating, it would be actually dangerous, okay? UV light is actually dangerous for us. It's ionizing. We already said it, said that in a previous problem in this paper. So it will be useless, okay? So you need the coating. All right. And 2, explain why the fluorescent lamp is dangerous if the fluorescent coating becomes damaged. So, if this happens, so UV light and mercury vapor can escape, okay? Okay, so mercury is toxic if inhaled. Okay, that's the first problem. And the second problem is that UV light is ionizing and can cause eye damage or skin burns. I mean, when you get tanning in the summer, and I come from Cyprus, so if you expose yourself in the sun, it's actually dangerous in the summer due to UV light. UV light is actually what creates, I think, the reaction inside our skin that makes our skin darker in the summer. Okay. All right. So this was a long paper. I hope I explained everything properly. If you find this content useful, let me know in the comments, leave some likes, please subscribe, and so on and so forth. And hopefully I will be back with more of these papers. Again, I kind of prefer the A-level papers because they're a little bit more challenging. And eventually, if this channel takes off, I will have hopefully physics videos of the higher level, but we will see. For now, good luck with your exams and hope these videos are useful. See you guys in the next video.